Sequences of numbers can be covered at just about any time in the calculus sequence. The only restriction really is that you need to cover them before you talk about series of numbers, which is quite natural because series are sums of sequences of numbers. However, sequences can also be used to investigate limits and continuity of functions, and that is something that we will allude briefly to at the end of this presentation when we substitute sequences into functions. That can be expanded, so if this is one of the first presentations you watch in calculus, then you will potentially use sequences to introduce limits of functions. If this is something that you watch after you have talked about limits and continuity of functions, then it is simply something where we look back at that concept one more time with from a different viewpoint. Either way, we need to start with the definition of what a sequence is. And a sequence, technically speaking, is nothing but a function f from a set of consecutive integers to another set, and for us that other set will usually be the real numbers. An infinite sequence is therefore defined on a set s, s plus 1, s plus 2, and so on of consecutive integers, where s is the starting index. A finite sequence is defined on a set of integers s, s plus 1, s plus 2, all the way to an integer t, where s is called the starting index and t is called the terminal index. In terms of notation, and that's something that we're also going to talk about on the next panel, it is customary to denote the f of k also by a sub k and call it the kth term of the sequence, and that is and the sequence is then denoted by ak, where k runs from s to infinity if the sequence is infinite, and by ak, where k runs from s to t if the sequence is finite. This notation is supposed to explicitly indicate that our sequence really is just a bunch of numbers that are given to us in a certain way, and that these numbers aren't necessarily aligned along an x-axis, for example. So sequences should be visualized as sequences. Well, duh, yeah, that's one of those terribly true statements. What am I trying to say? From a function point of view, well, if we talk about functions, we have an x-axis, a y-axis, and a sequence then is just something that maps the numbers 1, 2, 3, 4, and so on to outputs on the y-axis, and that is a perfectly good plot. However, when we talk about sequences as tools, especially when we talk about sequences as tools when we plug them into functions, it is much more beneficial to think of sequences from the sequence point of view, which is that we have an axis and we have on that axis somebody giving us a number a1. From that number we go to a number a2. From that number we go to a number a3. From there we go to a number a4, to a number a5, a number a6. You can see it gets a little squeezed here. From there to a number a7, and so on. So that a sequence eventually is a set of numbers where the numbers are revealed to us in a certain order, which is similar to what you do when you take a sequence of measurements, where you take repeated measurements or something like that, where the underlying time at which you take the measurement really doesn't matter, or in measurements for which it doesn't matter. For many measurements, the underlying time does matter, of course. Okay, as an example, well, the sequence 1 over k, k going from 1 to infinity, that sequence is called the harmonic sequence. And that means the harmonic sequence is the sequence of numbers 1, 1/2, 1/3. You can guess the next one is 1/4, 1/5, and so on. Which means, and future terms then follow the same pattern, which means the visualization is the harmonic sequence. If the 0 is here, the harmonic sequence starts at 1, the next term is 1/2, the next term is 1/3, the next term is 1/4, the next term is 1/5, and so on. In terms of connecting with functions, which we're not going to do that often, it is something where we have an interpolating function, because the interpolating function for the sequence 1 over k is of course 1 over x. Well, the values for the sequence are actually just the blue dots, or if you want to stay in the sequence picture simply on a vertical axis, then the sequence are the green dots that are being revealed to us here. They come around. Yeah, here's where the dots keep coming to us, and that's another way to visualize the harmonic sequence. The geometric sequence, 1/2 to the k going from 0 to infinity, and here's where you see why I didn't want to have a definitive starting index, because quite a few sequences start at 1 or at 0, and there are other sequences that we're also going to start at other starting indices. That one has the terms, well, the first one is 1/2 to the 0th, which is 1, the next one is 1/2, 1/4, 1/8, 1/16, 1/32, and so on. And that would mean that in the sequence picture, if 0 is here, we start at 1, the next term is 1/2, the next one is 1/4, the next one is 1/8, and that keeps going like that. So it's a very similar picture to what we have for the harmonic sequence, but the decay is faster, because 1/2 to the k, if you want to rewrite it, certainly decays faster than 1/k. Alright, finally, if a sequence is given by a formula, and I want to find the 15th term of the sequence -1 to the n times n divided by n squared plus 1, where n goes from 1 to infinity, and we should say here that k and n are typical sequence indices. I think I will use k for the most part for sequences, and I will use n for summation indices in series, but that is certainly not something that is uniform. Quite a few people use n overall. However, for this thing here, well, if I want to find the 15th term of this sequence, sequences are functions, we just plug in the number, right? So we end up with the 15th term being -1 to the 15th times 15 divided by 15 squared plus 1, which gives us -15 divided by, and 15 squared is 225, plus 1 is 226, so this is -15 over 226, and that's it. So that's not terribly hard. Finding higher order terms of a sequence will become challenging when we talk about recursive sequences, which will be in the next presentation. Okay, finally another definition. We will call a sequence strictly increasing if and only if for all k we have that ak is smaller than ak plus 1. So that's something where the next number is always greater than the previous number, and sensibly we call that increasing. A sequence is called strictly decreasing if and only if for all k we have that ak is greater than ak plus 1, so whenever the next number is smaller than the previous number. And if the sequence is either increasing or decreasing, then that sequence is also called monotonic or strictly monotonic. I'm throwing in the strictly here because even though in calculus for the most part people go with increasing, decreasing, and monotonic, because you have a strict inequality here, it sometimes is helpful to call these things strictly increasing, strictly decreasing, and strictly monotonic, because there are also instances where people will say increasing when the inequality could also include equality here if this was less than or equal. In this course we will call these things non-decreasing, non-increasing, and all that, and we will get to that when we need the definition. Either way, these sequences have the following properties. Well, an increasing sequence is a sequence where from A1 you have to go up to A2, then you go up to A3, you go up to A4, you go up to A5, and so on. There is no restriction on how large the increases have to be, so this thing could ultimately peter out, and that's something that we will need when we talk about the monotonic sequence theorem. But it could also happen that this goes off to infinity, which we'll talk about when we talk about infinite limits. A decreasing sequence is a sequence that starts at A1 and you go down to A2, then you go down to A3, and so on. So this is something that decays, and again this could peter out somewhere and the sequence could become almost stationary, have a limit, as that is called, or it could be that this thing goes off to minus infinity. A sequence that is neither increasing nor decreasing is something where there is no overall relationship that says the next number must be greater or smaller than the other one. As we can see here, this thing is jumping back and forth, but of course it need not be that it always just jumps back and forth. It could also be that it then has several jumps in one direction followed by several jumps in the other direction. Increasing and decreasing sequences will be important to us when we talk about the monotonic sequence theorem and when we deal with recursive sequences. Right now, let's just get used to them a little bit. if I want to prove that the sequence 1 minus 1 over k squared is increasing, well, I will have to work with inequalities either way, and I have two possibilities to do that. One of them is that I can simply look at the ratio of consecutive terms, and if I can prove that this ratio is smaller than 1, well, greater than 1, in this case, then the sequence is increasing, so that would mean I take ak plus 1, which is 1 minus 1 over k plus 1 quantity squared, divided by ak, which is 1 minus 1 over k squared. I find common denominators in numerator and denominator. Well, the common denominator in the numerator is k plus 1 squared, so I get a numerator of k plus 1 squared from here minus 1 from here. I get a divided by k plus 1 squared divided by numerator in the denominator is k squared minus 1 divided by k squared. Well, we know how to work out division of fractions. We multiply with the reciprocal of the denominator, so we end up with k plus 1 squared minus 1 times the k squared from here divided by k plus 1 quantity squared, which is this one, times k squared minus 1. And if we multiply that out, we get k squared plus 2k plus 1 minus 1 is k squared plus 2k times k squared plus 2k plus 1 from here, and k squared minus 1 here. And if we multiply all that out, well, we get k squared times k squared is k to the fourth, k squared times 2k is 2k cubed, k squared times k squared gives us k to the fourth, 2k times k squared gives us 2k cubed, k squared times minus 1 is minus k squared, and that's this minus k squared. 1 times k squared is the plus k squared here, and then we have minus 1 times 2k is minus 2k, and minus 1 times 1 is minus 1. These k squareds here cancel, of course, so we end up with k to the fourth plus 2k cubed divided by k to the fourth plus 2k cubed minus 2k minus 1. Clearly, because of these terms, the numerator is greater than the denominator, so this is greater than 1, and that means this sequence is increasing. Another way to work this out would be that we would simply have to verify the inequality. So we ask ourselves, is 1 minus 1 over k squared less than or equal 1 minus 1 over k plus 1 squared? That would mean, because we can cancel the ones, that negative 1 over k squared would have to be less than or equal than negative 1 over k plus 1 squared. When we cancel the negative signs, we have to be really careful. We are so far accustomed to working with equations where multiplying with negative 1 is not a problem. But one of the things that we certainly learn when we work with sequences, and specifically with increasing and decreasing sequences, is working with inequalities. And when you take an inequality and multiply it with negative 1, the inequality changes around, right? If you look at the number line, even though 1 is smaller than 2, when you multiply that with negative 1, you get that negative 1 is greater than negative 2, because negative 1 is to the right of negative 2. So here the inequality has to be changed around. So this works if and only if 1 over k squared is greater than or equal to 1 over k plus 1 squared. Well, I'd like to take reciprocals here. And again, when you take, first of all, I rewrote this. So this is the same as 1 over k plus 1 squared less than or equal to 1 over k squared. Well, now you want to take reciprocals. And when you take reciprocals, again, the inequality changes. 1/3 is less than or equal than 1/2, but 3 is greater than 4. So this inequality here works out if and only if k plus 1 squared is greater or equal than k squared, and this last inequality we know works. And so that means that this establishes, again, that the sequence is increasing, just with a different method. Note that a formal derivation would actually go in the opposite direction, because a formal derivation starts with something that is true, such as k plus 1 squared being greater or equal than k squared, and deriving from that this is true, that this is true, that this is true, and that this is true. As long as all the steps are reversible, we're going to keep working in this fashion here, however. Okay, so that takes care of this increasing sequence. Finally, a sequence is called bounded above, right? If and only if there's a number m, so that for all k we have that ak is smaller or equal than m. and it is bounded below if and only if there is a number m, so that for all k we have ak is greater or equal than lowercase m. So bounded above and bounded below just means there is some number that the sequence will never exceed above, and there is some number that the sequence for bounded below, there is some number that the sequence will not undercut. And a sequence is called bounded if and only if it is bounded above and below. And as an example, well, if we want to prove that the sequence 1 minus 1 over k squared for k equals 1 to infinity is bounded, well, we realize that minus 1 over k squared is never greater than 1 and always negative, because k starts at 1. And so that means that 1 minus 1 over k squared is greater or equal than 0 all the time. And similarly then, because we're always subtracting something off of 1, 1 minus 1 over k squared is less than or equal than 1. And that means that the sequence is bounded above by 1, and it is bounded below by 0. Okay, now we start talking about limits. And the informal definition of the limit of a sequence is that the sequence ak is called convergent to the limit L if and only if, for all sufficiently large k, we have that ak is close to L. Now this is something where we deliberately leave the terms sufficiently large and close to undefined. We're going to go with an intuitive and informal idea for limits. The details require epsilon and in definitions, which is something that you can see as you further progress into calculus, or also in classes called advanced calculus, where proofs take center stage, which is typically not the case in a first calculus course. In case a sequence is convergent to a limit L, we will write that the limit as k goes to infinity of ak is L, or that ak goes to L as k goes to infinity in this notation. And if the sequence is not convergent, we say that the sequence is divergent. The idea for convergent sequences is that your numbers a1, a2, a3, and a4, and so on that you get will continue and ultimately aggregate closer and closer to this limiting number L. But of course, it is not required that the numbers have to decline to the limit L. It could also be that your numbers bounce around a bit, like in this visualization, where as long as these oscillations get smaller and smaller and then aggregate around a limit L here, again we would have convergence. For divergent sequences, this kind of eventual aggregation does not happen, so it could be that your numbers just keep growing and growing and just blow up and never aggregate near any number anywhere. Or it could also be that, say, your a1 and your a2 go like this, but then your a3 is a1, your a4 is a2, your a5 is a1, your a6 is a2, so something that just keeps bouncing without the oscillation getting any smaller. If this goes on indefinitely, then that also is divergent. And finally, it could be that a divergent sequence just doesn't show any really good pattern in its behavior at all and just bounces around. As computational examples, and also as a cornerstone to ultimately work with limit laws, we note that the harmonic sequence 1 over k converges to 0. And because we don't have the formal definition as well as the axiomatic description of the real number system, the best thing we can say is that as we divide 1 by ever larger numbers, not be ever larger numbers. Okay, so now we divide 1 by ever larger numbers, and when that happens, then the value 1 over k gets ever closer to 0. That's about the best we can do. In terms of the visualization, of course, if 0 is here, we realize that the sequence starts at 1, goes to 1/2, goes to 1/3, goes to 1/4, goes to 1/5, and so on. And we can see that these fractions decline more and more and will ultimately aggregate near 0. Okay. The geometric sequence q to the k, where q is any real number, has the following properties. It converges to 0 for -1 smaller q smaller than 1, and that's because we're taking a number whose absolute value is smaller than 1, and we raise it to larger and larger powers. So we take fractions of fractions of fractions of fractions, if you will, so that goes to 0. It converges to 1 for q equal to 1 because the sequence is stationary, and it diverges for q smaller or equal than -1 and for q greater than 1, and that is something that we can also visualize. For q equals 1/2, we can see that the sequence declines very quickly. In the function picture, we have the interpolating function that just doesn't really flatten out, but it gets so small so fast that we don't see it being visibly different from 0 anymore. In the sequence picture, we see that the output values get really small very quickly. For q equals -1, we can see the same aggregation phenomenon, but because of the negative sign, things bounce around. And notice here that we don't have a good interpolating function because you can't really define good exponential functions with negative bases, so this really just has to bounce around like that, where then the sequence picture in green here makes a whole lot more sense. The numbers just jump up and down and ultimately aggregate at 0. And of course, when you have a base that is greater than 1, well, then your numbers get really, really large, really, really quick, and they continue growing at an increasing rate. So this is a sequence that diverges. Of course, you could say here, this looks like it goes to infinity, and that's what we'll talk about when we define infinite limits. Now, in terms of working with sequences, once we have these fundamental sequences, the geometric sequence as well as the harmonic sequence, we can talk about limit laws for sequences. And so if AK and BK are two convergent sequences, then the limit of AK plus BK is the limit of AK plus the limit of BK. Again, this is something that in an advanced calculus course, and sometimes also in a dedicated couple of class periods in a first calculus course, is something that people prove using the mathematically correct definitions, the formal definition of the limit. With the informal definition, we can simply reason that, well, if AK is close to its limit and BK is close to its limit eventually, then the sum, of course, has to be close to the sum of the limits. And then the same thing is true for the differences, and the same thing ought to be true for the products. When it comes to quotients, we have to be careful. So if all the BKs are not equal to 0 and the limit is not equal to 0, then we also have that the limit of the quotient is the quotient of the limits. And finally, if all the powers AK to the R are defined, then the limit of AK to the R is the limit of AK quantity raised to the R for an exponent R. Okay, so this is now something that we can use, and the typical trick to find the limit of a quotient, of such a rational quotient, if you will, is that we will always expand with 1 over k raised to the highest power in the denominator. So if we want to find the limit as k goes to infinity of 7k squared minus 2k plus 12 divided by 3k squared minus 15k minus 20, we realize that k squared is the highest power in the denominator, so we multiply numerator and denominator with 1 over k squared. That is because, well, this stuff goes to infinity and this stuff goes to infinity, and we don't know where infinity over infinity will go. However, if we multiply with 1 over the highest power in the denominator, what we get is the limit of 7k squared over k squared minus 2k over k squared plus 12 over k squared divided by 3k squared over k squared minus 15k over k squared minus 20 over k squared, which is just the limit of 7 minus 2 over k plus 12 over k squared divided by 3 minus 15 over k minus 20 over k squared. And now we know from what we know about the harmonic sequence that 2 over k, for example, will go to 0. We know that 12 over k squared goes to 0. We know that 15 over k goes to 0. And we know that 20 over k squared goes to 0. This is all coming from the harmonic sequence and the limit laws, right? 1 over k goes to 0, so 2 times 1 over k goes to 0 also. And if 1 over k goes to 0, then 1 over k times 1 over k, which is 1 over k squared, goes to 0. And multiplying by this 12 doesn't change anything, and so on. So this is something where people then also say we find these limits by inspection. If you've got a number divided by something that blows up, the limit is 0. That means the limit here is 7 minus 0 plus 0 divided by 3 minus 0, which is 7/3. We can also look at an example where stuff is a little bit scrambled, and so just because the k squared is in the front here doesn't mean it's the highest power in the denominator. Just because you've got a k cubed here doesn't mean that k cubed is the highest power. K to the fourth is what you want to use. And so then for the limit of 4k cubed plus 20k plus 1 divided by k squared minus 15k minus k to the fourth, you expand with 1 over k to the fourth. You end up with the limit as k goes to infinity. 4k cubed divided by k to the fourth is 4 over k. Similarly, you get 20 over k cubed and 1 over k to the fourth. And in the denominator, 1 over k squared minus 15k cubed minus 1. And you realize now this one goes to 0, 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 this one goes to minus 1, and so that limit is 0. If, perchance, you are watching the sequence presentation after, potentially long after you've talked about limits at infinity of rational functions, this is exactly the same process, so this should look familiar. If you're covering sequences before you start limits of functions, then this is preparation for limits of functions at infinity. The expressions can become a bit more complicated. So for example, I could also find the limit as k goes to infinity of 2k squared minus 1 divided by square root 3k to the fourth plus 15k. And if I want to find that limit, well, what is the highest power in the denominator? The highest power in the denominator is k to the fourth, but we take a square root of it. So the highest power in the denominator, if you will, is something like a k squared. So you want to expand with 1 over k squared, but in the denominator, because you need to put stuff under the square root, you want to expand with square root 1 over k to the fourth, and you can now see certainly that this is 1, which means, again, we have not changed the problem. If we now do the algebra, we get that this is the limit as k goes to infinity of 2 minus 1 over k squared divided by, and then here 3k to the fourth over k to the fourth gives us a 3, and 15k over k to the fourth gives us 15 over k cubed with the square root still in the expression. So that's the limit of 2, or that is 2 minus 0 divided by square root of 3 plus 0. Okay, this limit actually shouldn't be there. That is genuinely a typo. However, it is not incorrect, because the limit of this is the same as the limit of this, because they are both 2 over root 3. Okay, so this is something where I'm taking a dive because I don't want to interrupt and edit again, but this is also something where technically, if you were to put this as an answer on a test, I couldn't really deduce anything, because technically it's right. Nonetheless, when you go from the limit to the numbers, you don't want to put the limits down. So this really shouldn't be there anymore. Ultimately, as a number, if you want to rationalize, this is 2/3 root 3, and that is the finishing touch for this problem. And now, as a quick theorem, if we want to compare polynomial growth k to the r with exponential growth a to the k, then we can say that for real numbers a greater than 1 and r greater than 0, we have that the limit as k goes to infinity of k to the r divided by a to the k is 0. So exponential growth beats polynomial growth. This is something that in calculus, once you have derivatives, or after you've had derivatives, you may have already seen it, people do this with L'Hopital's rule. We could work it out here without any of these more advanced tools, because we can say the following. If we're looking at the ratios of consecutive terms, then that limit is the limit of k plus 1 to the r divided by a to the k plus 1 divided by k to the r divided by a to the k. You know how that goes. We simplify by multiplying with the reciprocal of the denominator. We end up with the limit of k plus 1 to the r times a to the k divided by a to the k plus 1 times k to the r. A to the k over a to the k plus 1 is just 1 over a, and k plus 1 over k goes to 1, and if we raise it to r, it still goes to 1. So this limit is 1 over a, which is smaller than 1, because we said that a was greater than 1, right? So that means there is a number q smaller than 1, so that for large k, say for all k greater than capital K for an appropriate capital K, we have that this ratio is smaller than q, which is smaller than 1. What does that mean? Well, that means that k to the r divided by a to the k is smaller than q times the previous term, k minus 1 to the r divided by a to the k minus 1, which is then smaller or equal than q squared times the previous term from that, which is k minus 2 to the r divided by a to the k minus 2, and so on all the way to q to the k minus capital K times k to the r over a to the k. And now we realize that when lowercase k goes to infinity, we have a number smaller than 1 that is raised to larger and larger exponents. So this goes to 0 as k goes to infinity, and that's what we wanted to prove. So this is another way to establish that exponential growth is a whole lot faster than polynomial growth. Let's come to infinite limits. We will say that a sequence grows beyond all bounds or goes to infinity in symbols ak goes to infinity as k goes to infinity, or limit k going to infinity of ak equals infinity, if and only if ak is arbitrarily large for all sufficiently large k. Again, this is not a mathematically formal definition, this is an informal definition, but I think we can agree that sequences such as k, or 2 to the k, or the logarithm of k to base 2, which of course grows very slowly but nonetheless does grow beyond all bounds, that all these sequences go to infinity. Once we have that, we should also note that sequences that go to negative infinity are defined similarly, and we're not going to do that here. That's something that is actually a good idea for you to fill in the definition for yourself, to actually get further accustomed to mathematical language. Okay, as an example, find the limit of, as k goes to infinity, of 4k cubed plus k minus 10 divided by 15k squared minus 5k plus 4. We're going to use the same approach as we did before. We simply expand with the reciprocal of the k to the highest power in the denominator, so we expand with 1 over k squared. And that gives us the limit as k goes to infinity of, this time 4k here, plus 1 over k from here, minus 10 over k squared from here, divided by 15 from here, minus 5 over k from here, and plus 4 over k squared from here. And we realize that that is infinity plus 0 minus 0 divided by 15 minus 0 plus 0, and that is infinity. Okay, now look, one of the things that you may have seen in a pre-calculus class when you computed horizontal asymptotes of rational expressions is that there is a theorem where you can memorize what happens when various powers line up in various ways in the numerator and in the denominator, and that theorem gives you the horizontal asymptote, respectively the limit, directly. I would always say rely on your computational skills, because those skills ultimately will help further than certain theorems that are very, very specialized. Now, to be sure, there are theorems that you want to and should memorize because they are fundamental, but a theorem that gives you a limit at infinity in one special case is not one of them, and so then remembering the computational approach, trust me, really is a lot more beneficial. And so the only thing that you want to remember there is expand with 1 over k to the highest power in the denominator, and then go through the computation. It'll always give you the limit, because it'll either give you number over number, where the denominator is not 0, it'll give you 0 divided by a non-zero number, or it'll give you infinity divided by a non-zero number, and in either case you can conclude what the limit is. With that, I think we're now closing out with this idea of plugging sequences into functions. So for the function f of x equals x squared minus 9 divided by x squared minus x minus 6, and the value x0 equals 3, I want us to compute the limit as k goes to infinity of f of x0 plus 1 over k, and the limit as k goes to infinity of f of x0 minus 1 over k. Now what you notice here is that x0 equals 3 is actually a forbidden point, because if you plug in 3, you get 9 in the denominator minus 3 minus 6, which is 0, and we cannot divide by 0. If you've seen limits of functions before, then you realize, yes, this is essentially a limit computation, and it makes sense because the numerator is also 0. If you haven't seen limits of functions before, and even if you have, another way to investigate such points where you've got these divisions by 0 is that you simply add and subtract a sequence that goes to 0 so that you can see what happens as you approach the point without actually evaluating at the point. And so here we would take the limit as k goes to infinity of f of x0 plus 1 over k, which is the limit as k goes to infinity of f of 3 plus 1 over k. Well, that must mean we plug in 3 plus 1 over k for x. So we get the limit as k goes to infinity 3 plus 1 over k quantity squared minus 9 divided by 3 plus 1 over k quantity squared minus 3 plus 1 over k minus 6. We multiply that out. We get 3 squared is 9 plus 2 times 3 times 1 over k, which is plus 6 over k, plus 1 over k quantity squared, which is plus 1 over k, minus 9, divided by 9 plus 6 over k plus 1 over k squared, because that's just 3 plus 1 over k quantity squared again, minus 3 minus 1 over k minus 6. We see that the 9 minus 9 goes away here. We also see that the 9 minus 9 goes away here. So we end up with the limit as k goes to infinity of 6 over k plus 1 over k squared in the numerator, divided by 5 over k plus 1 over k squared in the denominator. Well, this one, if you just memorized that theorem that I mentioned, then this one looks kind of weird. But here we just go ahead and multiply by k to get numbers again, right? And so we end up with the limit as k goes to infinity of 6 plus 1 over k divided by 5 plus 1 over k, which is 6 plus 0 divided by 5 plus 0, which is 6/5. And if you do this with the limit as x of f of x0 minus 1 over k, you get the same story, only that you plug in 3 minus 1 over k, which means that your multiplication gives you a minus 6 over k plus 1 over and a minus 6 over k here. Everything else stays the same, so you end up with the limit of minus 6 over k plus 1 over k squared divided by minus 5 over k plus 1 over k squared. Again, you multiply with k, you end up with the limit of negative 6 plus 1 over k divided by negative 5 plus 1 over k, which is negative 6 plus 0 divided by negative 5 plus 0, which is still 6/5, which means that if you approach from the left or from the right with an addition and a subtraction of 1 over k, you get the same limit either way. Now, that doesn't necessarily say that the function itself has a limit at that point, but what it does say is that as we plug in input sequence and input approaches the forbidden point from the left as well as from the right, you have that the outputs aggregate at the same height as we can see here, and that is the idea of continuity of a function, except that for continuity of a function you can't just connect everything to the sequence plus 1 over k and minus 1 over k. You would need to connect that with arbitrary sequences that go to 0, and then you would go with x0 plus hk and x0 minus hk, for example. Other than that, as I said, sequences, because of this type of example, which can be expanded, are another way to examine limits of functions at a point, but that would certainly be something for another presentation. We have familiarized ourselves with sequences and their limits in this presentation. You will probably have some homework problems where you have to compute limits of sequences. Remember, you expand with 1 over k to the highest power in the denominator. If you look back at this example, if the highest power in the denominator is a negative power, you still did that because that's what the multiplication with k did in the computation on this the previous two panels here, 2 panels before the animation, okay? But either way, the computations shouldn't be too bad, so go ahead and take care of them, and then let's take a look at recursively defined sequences.